This video is going to pick up where the last video left off, and we'll take a look at some more involved list Prolog predicates. Starting with the selects predicate. Selects L and R, I suppose. This is true where, let's type this way, true if L is a subset of R. That is to say, if all the elements in list L are also in list R in no particular order. It's worth mentioning at this point, Prolog doesn't like it when you rename some of the built-in predicates, and subset already exists, so we have this name for it. So the idea here is we want to walk through each one of these items, or through the items in L, and see if they can be found in R. And if so, then we want to get rid of that item and then look for the remaining items. So as it turns out, we have a very handy predicate for this. The del predicate here will allow us to remove an item from this L. So if we pass L in as this target item here, or even as, sorry, if we pass one of the items from L as in the target item here, and if we remove that item from our list R, let's say here, then what we're left with is the list R minus that one item. So if it succeeds, it'll successfully remove the item and give us back the remaining items so that we can continue to remove. If it doesn't exist, then del will fail, and we can say, well, then there's an item in L that isn't in R. So the base case for this selects is if we have an empty list as our input, then it doesn't matter what the output is. The empty list is the subset of any list. Okay. The recursive case, on the other hand, we want to separate the head from the list of our sublist, let's call it. So we got call it H pipe T here, and we have let's just have it as L. Let's call it R since it was there before. Okay, so then we've removed, or we've separated the head from the list, or from the tail of our input sublist. So now let's see, can we remove that head from the outer list, the super list here? So in that case, we're going to say del H from R, giving us some sort of new R. We'll call it R1. Okay. So this will only succeed if we can successfully remove H from the list R, and that'll give us back R1 so that we're not continuously removing the same item, right? If we have the subset, if we have the list 1, 1, 1, 1, 1, 1, and we're asking, is that a subset of the list 1, 2, 3? That should be false, so we need to have, once we remove the first instance of 1, we shouldn't have 1 left in that list anymore. We should have that one now gone, and now we have a list with 1 fewer element. All right. So let's see, can we now remove all of the items in the tail from what's left of this list? So recursively, we ask selects tail from R1. And if that's successful, then good. So the key here is that we have this del predicate that's already built in, or sorry, that we built in the previous video, to see whether or not we can successfully remove an item and get back this new list with 1 fewer item in it. So let's just test this out. Lists. So we could say, for example, is the empty list selects empty list a sublist of A, B, C, D, E. And sure enough it is. We'd ask, is BC or a sublist of A, B, C, D, E? And it should be, and it is. We could ask CB, so in no particular order. That's also true. And then we could ask something that isn't. So for example, AA shouldn't be a sublist because there's only one A in the bigger list here, and that comes back false. So that seems to work fine. All right, so that's the end of selects or sublists. Let's move on to the next one, which is sorting. So sort, which takes in 2 lists, call it L and R again, is true if R is the sorted version of list L. So in this case, we're passing in some unsorted list L, and we want it to be sorted by this predicate, and that will be yielded into the variable R. So again, sort already exists, so let's rename this my sort. Now, my sort's just it's going to be an insertion sort algorithm. So the idea is we're going to recursively sort one item at a time. So we're going to start by CDRing down this list, shrinking it down until there's nothing in that list, and then we'll add the items into the list, one item at a time, in sorted order. So we're going to need a helper function called the insert function. But let's create the sort function first. So my sort. Base case here is that we have an empty list, and an empty list is already sorted, so that's easy done. In the recursive case, though, we're going to say my sort takes in some list, but we're going to pull it apart to a head and a tail, and we'll have some sort of result list here as our answer. Now what we're going to do is just CDR down. So my sort is going to call my sort on the tail of the input list to give us some sort of sorted tail. Let's call it sorted tail. So we can sort the tail using this, and that's just going to call my sort and CDR down and CDR down and CDR down. Eventually we'll reach this point here where the tail was the empty list, so the sorted tail will be the empty list. Now all we need to do is insert that item back in sorted order. So we can say insert the head that we took off at this iteration into the sorted tail, assuming we have some sort of insert function that can add it in place, and that will yield the result. So insert, we need to create still, should be a function that takes in an atom and a list and returns the atom added into that list in sorted order, where we assume that the input list is sorted. All right, and that yields a result, which we then pass on to the previous call. So the issue now is we need to create an insert function. So the idea behind insert, we're going to assume again that second arg is a sorted list, and we're just going to CDR down until we found a spot for the key. So we're going to start by comparing the key to the first element in that list. So we're going to have a list, let's say, let's just put a bunch of odd numbers here, 3, 5, 7, 9. Okay. Now, if this is our list and we want to add the item, let's say 1 into this, so we say insert 1, 3, 5, 7, 9, then we expect that to be, this is not actual code, we're expecting that to be the result 1, 3, 5, 7, 9. Okay, so it just adds it to the front. But if we wanted something maybe a little bit more involved, like insert the number 6 into the list, 3, 5, 7, 9. There we go. We have to do this one element at a time, comparing 6 to 3 and 6 to 5, and then finally 6 to 7. Now, by human standards, it's pretty easy to determine where that 6 should go. So we got 3, 5, 6, 7, 9. But by programming standards, we might have to think for a second to realize what the comparisons will be. So if we compare 6 to the head of this list, it's going to be too big, which is to say we want to CDR down until the front of this list looks like this. And at that point, when we compare 6 to the head of this list, the head is bigger. So the item's going to be smaller or equal to the head of the list. So at that point, that's where we want to actually do the cons. And we can stop CDRing down and join that as our result. Okay, so at that point, we'd take that and we'd say 6 pipe that. And then on the way back up, as we've seen before, we can add these items back into the list using a notation similar to what we have up here, h pipe r. All right. So let's start off with our base case. Base case 1. So insert. So for insert, if we have an empty list, that's pretty straightforward, right? If we just CDR down, let's say we have the largest possible item, so we want to add in, let's say, a 10 here, then we're going to compare all these items till we get to an empty list. At that point, we can add this item in. It will just be added as the very last item. So if we have some item that we want to insert into an empty list, then we just yield the list with that item. So square bracket x square bracket. So this is a list with exactly one item, which happens to be the item that we're trying to insert. So that's a pretty good base case. So that's if the list is empty. So if the list is empty, then we add that in. Okay. Otherwise, now we have two other cases here. So we have the situation we're comparing all the way down this list. In one situation, let's say this first situation here, 6 is too big to be inserted at the head of this list, so we need to CDR down. So that will be our recursive case. The other case here, when we're comparing, let's say 1 and 3, 1 belongs at the front of this list, right? We can see that 1 is smaller than the head of this list, so we can stop searching and just put it into that place. So that'll be our other base case here. So we have insert some item, we call it x, I suppose, onto some list, h pipe t, and that's going to yield x comma h pipe t. So if this is the list that we're adding it onto, x is the item that we want to add into that. Now we only want to do this in one condition, that is the condition that the item we're adding is smaller than or equal to the existing item there. So we're going to say x is equal to or less than h. All right. So from there we can take, there's our other base case. This is a success base case, we could say, or I guess they both are. So found the spot, I suppose. Otherwise, we have to go looking for that spot. So insert x into some list that's h pipe t. So we're going to be peeling this h off, and now in this case, this won't be the case. X won't be less than or equal to, so we're now looking at the, let's say, 6 compared to 3 case. So h is going to be too small, so we're going to have to throw it away, but we don't want to get rid of it forever. We want to later on attach it to our result. So we'll say h pipe result as our result variable here. Now, in the recursive case, we need to make sure 2 things. First off, that our item is in fact bigger than the head, so x is greater than h in this case. And then what we'll do is we'll just recurse into insert. So we'll say insert x into the tail, yielding r. Okay, so that's x inserted somehow into the tail. Maybe it's the base case and it just gives back a list with 1 item. And then on the way back up the recursion, we're going to take all the heads that we threw away and attach them to the result in order. So let's test this out. So let's start by just testing the insert function. So we have insert, we saw 1 into the list 3, 5, 7, 9, giving us r, and we can see that adds it to the front of the list. And similarly, if we want to add 6 into that list, it adds it later on into that list. So it CDRs down using our recursive case until it finds a point where the item we're adding is less than or equal to the head of our list. At that point, it cons it into place. So notice this slightly different syntax here. We have x comma h, just says create a list where h is in the list and x is in that list in this specific order, and then join that to everything else that was there. So this h pipe t is kind of what we got as our input here. So kind of the situation, this would be h pipe t joined together, and then we're just going to say put an x in front of that. Okay. So insert seems to work. Let's test out our sort then. So we have my sort with some list. Let's say the list 7, 4, 2, 8, 1, 9, 5, and then a double, and then another 2. And that gives us in sorted order. And as we can see, it is in sorted order. All right. So that's the insertion sort algorithm. There's other sorting algorithms available as well. I recommend trying some out. See if you can't code some other familiar ones like a bubble sort perhaps, or some others. Right, let's move on though to max. So if we want to figure out what is the maximum of a list. So we have maximum, what is the values here? List and result. So this is true if the number, we'll say, r is the largest value from the list L. So maximum, we put in a list and we get some sort of result, in this case just a number. Now there's 2 different ways we could solve this, recursively or iteratively. I'm going to solve the iterative one here and leave the recursive one as quote-unquote homework for you guys to solve on your own. I do recommend trying it out. It's not much different than this solution though. So the general idea we're going to do is a linear search. We're going to look for the largest. So we have to traverse through this list L. We're going to CDR down that list, or peel the head at each iteration, keeping track of the biggest item that we find so far. So we're going to need another variable slot to keep track of that variable, and we're just going to take the largest item we have and then compare each new item to that largest so far. If the new item's bigger, we'll pass that forward. If it's not bigger, then we'll pass the old biggest forward. Okay. which means we can't use this this public version maximum. So we have maximum with 2 elements, which is a list and some result. We'll call it M for maximum. That's going to have to call some 3 version of this predicate. So we'll say maximum, where we pass in the tail. We'll take head as the largest so far, so that way you don't have to do a comparison for one of these values, and then M will be our final result. So we take the entire list here as h pipe t, we pass the list t forward as the remaining results, and assume that there's at least one item in there, and that will be the largest so far. So for this problem, we're going to assume that there's at least one element in this list, which is fair. If somebody asks you for the maximum of an empty list, you should get false as your answer, and Prolog will manage that for us now. All right, so the base case for this 3-item list, since we're doing an iterative approach, follows a similar pattern to other iterative approaches. Base case is now we've run out of items because we've checked all of them, which means the value in this next slot is the largest so far out of all of them, or the largest overall. At that point, we just move it over or unify it with this 3rd spot, which is our result variable, which will be unbound until this point. Okay. Now, in the recursive cases, there's 2 situations, right? Because we're doing a comparison. We're going to take the head off of this list, and we're going to say, in one case, the head is bigger than the biggest so far, in which case we pass it forward. In the other case, it's not bigger than the biggest so far, and we can pass the old biggest forward. But they both look similar, so we have maximum of some list, h pipe t. We have our largest so far, I'll even call it LSF for largest so far, and our overall maximum. So if the largest so far variable is greater than the head, so if head is equal to or less than the largest so far, then what we'll do is we'll pass the largest so far forward. So we'll say maximum on the tail. We still need to check the rest of the items. But largest so far was bigger than head, so we'll pass largest so far forward. And then M remains this unbound variable to create a link between the base case and our original call. All right. That's one recursive case. In the other recursive case, maximum head pipe tail, and oops, there we go, and largest so far, and our maximum final result. And then in this case, it's just the other comparison. So head is strictly greater than largest so far, and in that case, we'll pass it forward. So in one case, LSF is bigger, so that's what goes forward in our counter, or our temporary best so far variable. In the other case, head is bigger, so that's what we'll pass forward. In either case, when we come back to the next iteration, the thing here is the biggest that we've seen so far. When we get through all of the items, then the thing in this slot is going to be the biggest out of all of the items. All right, let's test this out. So save lists, maximum of the list 427183, no particular order, is R. There you go. 8 is the largest value. We can backtrack, ask if there's a different larger value, but there is not. All right. Again, this was the iterative approach, and I highly recommend you try to work out the recursive approach here on your own time. Okay, let's do some more practice problems here. What if we wanted to find if a list has an even number of elements? So we call this even list is true if, say even list 1 is true if its argument is a list with an even number of elements. So again, this structure here doesn't mean we're calling it even list with a slash in it. This is even list is a functor with arity 1, and then we're going to use that to determine whether or not a list has an even number of elements. So as a hint, we don't need to use mod to solve this, and I recommend again pausing the video, see if you can solve this on your own, but here comes the solution. So for this, a base case would be that an empty list will consider 0 to be an even number, so even list empty list, that's just a fact that is true, right? The empty list has an even number of elements. We could also argue a list with 2 elements in it has an even number of elements. So we could say square bracket, we don't care what those 2 elements are, item 1, item 2, or underscore underscore. That has exactly 2 elements. Now that's not strictly necessary because we can probably get it down to this empty case, but it helps us to understand what we're doing. So a list with 2 elements also is an even list. And then if we have more than that, if we have more than 2 elements, then we're going to unify with a list that has at least 2 elements, but maybe more. Call that tail. And this will be true, right? So maybe there's 3 elements. Maybe tail has only 1 element in it. But what we'll do is we'll pass that down to even list on just the tail. So the entire list is true if we can remove 2 items. Sorry, the entire list has even numbers. If we can remove 2 of them, and what we're left with is still an even list. So that eventually will bring us down to one of these 2 base cases, and we'll have true or false. If it doesn't reach one of these base cases, for example, if it reaches a situation where we have exactly 1 element, that won't unify with any of these cases, and it will return false. But otherwise, this will tell us if we have exactly 2. Save. Lists, and we could say even list 1, 2, 3, 4 should be true. Oops, and even list 1, 2, 3, 4, 5 gives us false. Good. All right, so that's one problem. What about instead of checking if we have an even number of elements, we check if every element is an even number. So we could say all even /1 is true if its argument is a list with all even numbers. Now for this, we'll assume it's all numbers, so we don't have to worry about determining the type as well as determining if it's an even number, but we do need to determine if those numbers are even valued. Okay. Now again, we'll assume an empty list is true, so all underscore even is all of its not numbers are even, so all the numbers that it has are in fact even because it doesn't have any numbers. The recursive case in this case is that we need to walk down this list 1 element at a time, checking every single one against the number 2 to see if it has no remainder, as say to use the modulus operator. So all even head pipe tail is true if we can do a calculation here. Say the remainder is h mod 2. So mod is the built-in modulus operator. And now we need to know if remainder equals 0. And if that's the case, then we'll call all even on the tail. So this just checks 1 item at a time. If it has an even value, great, and then continue on with the rest. So a real simple pattern for processing lists 1 element at a time. All even, let's see here, 1, 2, 3, 4, 5 should give us false, and all even 2, 4, 6, 8, 10, true. Hooray. All right, let's get into a couple more big problems here. Next is the idea of accumulators. So we saw accumulators were an important design pattern when we're dealing with scheme lists, and it's true of list processing in any language. So how can we create a sort of accumulator pattern when we're dealing with Prolog lists? Well, as it turns out, we've already seen a similar thing. Scrolling all the way up here, our length predicate up here determined the length of a list by using this accumulator variable. We saw that both in the recursive version and in the iterative version, where we had this one variable just taking on new values over and over and over again and summing things up. Similarly, in our recursive version, we had, where was it? M was taking on a value, we'd defer that value and return that. So we were accumulating up the length of this list by summing up ones. So for example, we want to sum all the elements in a list. So call this sum. Say sum /2, better yet, sum L comma R is true if R is the sum of all elements in the list L. Which is to say we want to sum up all these things. So let's solve this recursively first. So the sum of an empty list is 0, makes a pretty good base case. Then we want to take the regular case and break it down to the point where we have an empty list so that we can get our initial value 0, and then going back down the recursion, do up all the sum operations that we deferred as we were traversing down the list in the first place. So in our recursive case, we have sum h pipe t. some value r. Now we need to figure out what that value r is. I mean, first things first, we can determine, is this thing even a number? So number h, good to know, I suppose. Not mandatory, we could assume in this case, but it's best not always to assume. So that's true if h is bound to a number, as we've seen. And then the next thing, we just need to CDR down the list. So sum the tail gives us some sort of partial sum. Okay, that's the sum of all the tail. And now all we need to do is just add the value of the head into the tail. So r is partial sum plus h. Okay, so we add all these values together, so just recursing down and then adding these things back up as we come back. Right. That's the recursive version. We'll test that out, but let's also try out the iterative version as well. Sum it. Now with most iterative versions, as we've seen, we need to have some extra variables. We need an accumulator variable to keep track of the information as we're moving forward through the list. So we're going to have some list and some result, and that's going to be true if the sum helper is true, and that has list, an initial value for our sum, and that same result. Okay. Now the base case for most iterative functions, sum helper, for most iterative functions, the base case is when we reach that base case, in this case an empty list, we've done all the work, then we have some sort of accumulator variable s that now has the final answer, and you just move that over into the last column there. So this middle column here is going to start off at 0, and we're going to add one item to it over and over and over again. When we get to the very last value, we'll move that into this last slot here, which unifies with this unbound variable r, passing that value back through the recursion to the calling function, or to our query in this case. All right, so that's our base case. That's our base case. So for our recursive case, sum helper, we have a non-empty list, so h pipe t. We want to take one of those items and add that into this slot. So we currently have s as our value so far in this slot. Actually, we'll call it a for accumulator and s for the final sum. And then all we need to do is take the current value of h and add that to our accumulator. Give us a new accumulator, say a1 is h plus a. So if this is all the values that we've added up so far, we're going to add in this new value h to give us a new sum. Now we're just going to take that new sum and pass it forward. So sum helper on the rest of the values that we have with this new accumulator variable, and then this unbound variable s, which again is just creating a link between the calling function and our base case. Okay, let's test both these out. So we have lists, and we can say sum the list 1, 2, 3, 4, 5 is r, and similarly sum it the list 1, 2, 3, 4, 5 is r. There you go. So we can add up both, we can do accumulators in both of these. This one isn't too new. We've seen similar issues before. It's just worth noting that the accumulation problem can still be used in Prolog, or solved in Prolog. All right. And now one last general purpose solution is the idea of mapping. So the general idea of mapping, as we've seen before, is we have this list. We want to apply some sort of function to every item in that list. So a simple example is trying to scale every number. So we're mapping, let's say, ×2 onto every item in the list, giving us a new list where all the elements are mutated by that function. So in this case, all the items are doubled. So general idea is we need to CDR down that list, applying the function to each item as we're going, and then collins everything back up at the end. So let's do a scaling example. First, we'll just scale everything by a constant factor. So we can pass that constant factor in as an argument. So we'll say scale, which takes in some sort of constant factor. We'll call it x, a list, and a result. I'll make this a comment first. Is true if r is the list of all elements in L scaled by the constant x. Okay, so if x is 2, then we're going to take in a list of numbers and double them all to get r. So base case for this, for doing a recursive approach, the base case for this is, this is an iterative approach. That doesn't make a difference. Okay. The base case for this is that our list is empty. If we have no items to scale, then we don't have to do anything. So scale, we don't even need the constant in that case. We have an empty list, so our result is the empty list. Now the recursive case is we want to take one item at a time, scale it, attach that to our result, and then recurse down the rest of our list. So we'll say scale for some constant. We'll call this x again. We have some list, so h pipe t, we need to pull that list apart. And then we're going to have some sort of result. I'm just going to call this r for now, but we're going to have to change that in a second. So once we have our scaling factor x and our input value h, we're going to multiply them together, so x times h. And we'll say that's, we need a new value for this. This is the multiplied value, so we'll call it h1. It's the new value for h. And h1 is x times h. So we scale one value at a time, and then when we have this value, we're going to want to return it into the result list. So we're going to say h1 pipe r. Okay, so we take the value off from here, multiply it by x, and then on the way back, as we've seen before when we were dealing with the join function, we can see all of these conses. The new value that we're multiplying is going to be joined with the result, and that result will get populated later on, and we'll end up having this large cons situation. All right. So our call is scale, and then constant just passes through. We're scaling the tail here to get the result r. Okay, so take the head off of our list, multiply it by our constant to give us a new value. That new value is going to get consed on to some result, but that result doesn't get determined until we call scale on the tail. All right, let's test this out. So we have scale. Let's just do 2 for the list. 1, 2, 3, 4, 5 is r. That scales all the values, 2, 4, 6, 8, 10. All right. So this is not a new pattern for us, being able to map through things. It looks a little bit different in Prolog, but it's the same idea. We CDR down, so CDR is kind of happening here by unifying this with a proper list. It's splitting parts of it apart. And then we cons back together, and that says take the result list and attach one new item. So the way we split apart, we sort of join together in the same way. Now, as we're scaling or CDRing down, we're doing some sort of function here. In this case, we're doing a multiplication of a constant factor, a scaling operation, but it doesn't always have to be scale. We could do a general purpose function using some built-in operations. So let's create a square functor here. Square x gives us x2 is true if x2 is x times x. Okay, so a little square function. So it takes in some value 3, let's say, and returns 3 times 3, which would be 9. Let's test it out first. Lists square 3 is x, x is 9. Okay. So we're going to use this and map this function, this general purpose square function, across all of our input lists. So we're going to have a general purpose map now. So map works similarly. It takes in some sort of constant or function and a list and a result list. So actually I can type this out. Map FLR is true if R is the list of all elements in L, say mapped by F. So mapped through F, we've applied F to each element in L to yield the list R. So in the base case, we don't care about the map because we have an empty list, so the result is just an empty list. But if we're not at the base case, then what we need to do is similar to what we've done before, CDR down, cons back up, and apply this function f. So we have map, we have f is our whatever function. In this case, we're going to pass square into it. We have our list, which we need to peel apart, so h pipe t, and we have our result, which we'll call x pipe r. Okay, so x is going to be the result of applying h to f. Now the way we do that in Prolog in the general purpose sense is to use what's called the call predicate, and call takes in some sort of functor and the argument for that functor, and returns the result of applying that argument to that functor, so x in this case. So it takes in the first two arguments here, so the name square and the value for x, and it yields back the result variable. Okay, so there's those, and we can say map. Now for map, the recursive case here, we've already mapped h into x, and then we've attached x onto the result. So now we just need to call this on the tail. So we pass f, the tail of our input list, and r is the result of mapping f across that tail. So same pattern as before, but instead of multiplication and is, we have this call operation. And if we want, we can test this. Call lists, and this was map. We're going to pass in square and the list 1, 2, 3, 4, 5, 6 to get the list r, and we get the list of squares. Pretty interesting. All right. Yeah, one last example here. Let's see how we can apply this same idea, that is to say mapping, onto situations where our lists aren't necessarily flat. So let's try doing a tree map, or in this case, we'll just deal with a tree scale. Now, to simplify the arguments, I'm just going to assume that we're just going to double a tree. I'm going to call it tree scale in the general purpose, but I'm not going to bother passing through a constant. I'm just going to multiply everything by 2. So we need some sort of tree scale. So tree scale, it's going to take in some t and return some sort of result. Is true if r is the nested list, i.e. tree, containing all elements in t, but doubled. It's times 2. Okay. All right. So a base case for this is pretty similar as before. Tree scale of some empty tree is just the empty tree. Great. We had no items. We scaled them all. But the rest of the work is going to be similar to what we had to do before. We want to map through each one of these items, but we have an extra case in there where, as we saw in Scheme, we can't assume that the item that we're looking at, that is to say the head of our list, is in fact a list or an atom. We have to determine which one of those two things it is. So if it is a list, then we want to tree scale across that list, because it may be a nested list as well. Otherwise, if it's just an atom, or just a number rather, then we can just do the multiplication right away. So we have tree scale. I had capital S in the notes, so let's do that. Tree scale of two things. We have head, pipe, tail as our input. I'm going to just leave this blank for now. We'll fill it in with what we need to, with what we find we need to know. So as I said, there's two situations. One where we're dealing with just a number, one where we're dealing with a list. So let's deal with the number one first, because it's a bit easier. So if h is a number, then we can pretty much do what we did before. We just multiply h by a constant and then scale down the tail. Right, so we say the result for head is h times 2 in this case. If you want, you can pass x through here and multiply it by x. It's about the same design. So that gives us h multiplied by 2, and then we still need to scale the rest of our list. So we'll say tree scale t to get result tail. Okay, so now we have result head and we have result tail, so let's join those together to get our final result. Result head, pipe, result tail. Okay, so if it was a number, it's pretty similar to what we did before. We multiply that number, we scale down the rest of the list, and then we join the two results together. On the other hand, maybe it's not a number. Tree scale h pipe t. In fact, this is actually going to have the same pattern up here, RH pipe RT. So the question is, what are RH and what and RT? So if our input is not a number, then we have to use the is list predicate. So let's just test this real quick. Is list for some list is true. Is list for some number, for example, gives us false. So it's just a Boolean predicate to determine, is this thing what it says it is, the type of this value. So in this case, we want to say if our head is a list, then we want to treat it like a list. We don't want to try and multiply that list by 2. Instead, we're going to call tree scale to do that to every element in that list. So we'll say tree scale on head will give us the result of scaling the head. And tree scale on the tail will give us the result of scaling the tail. Okay? And then we take those two results, result head, result tail, and we join them together as we did before. Okay? So split them apart, join them together using the same pattern. Whether or not it's a number or a list, we still need to attach that together. We still want the same structure of the tree. So if we're taking it apart using a flat pipe, then we'll do the same thing here. The only key difference is if it's a number, we multiply. If it's a list, then we treat that list the same way we treat any other list, by scaling it. Let's test this out. I don't think I have any specific demo, so lists and tree scale. And let's just create a list here. So a list that has 1, 2, 3, comma 4, comma 5, comma 6, 7, 8. There. So our result list should have that exact same values, or sorry, that exact same structure with all the values doubled by 2. So 3, 1, 2, 1, 1, 1. Good. And they're all doubled, so it seems like it works. So there's the basic idea. It's the exact same idea we learned for scheme. If we want to scale across a non-flat list, or in any kind of traversal across a non-flat list, we have two cases. So in both cases, we take the head from the list, and we recurse on the tail, but then what we do with that head depends on, is this thing a list or is this thing a terminal value, a number in our tree scale example. If it's a terminal value, then we treat it as though we would have treated each element in a flat list. And if it's not a terminal value, if it's a list, then we treat it the same way we treat the tail. So we don't have to create some sort of special function to treat the head. Just check if the head's a list, treat it like a tail. If it's not a list, then treat it like just an element. And in all cases, join your results back together. All right. That about does it for all of these list processing Prolog predicates. I'll be back with one last video, let's say cuts in Prolog, in the next video.